So in the last video, we saw the bad news, that differential equations are hard. Not all of them are prohibitively hard, and we'll certainly solve many of them in this course. But if I give you a random differential equation, you're unlikely to be able to solve it, even if you know a lot about differential equations. Some people spend their whole lives solving differential equations. The good news, a couple pieces of good news. One, we'll focus on a few specific methods in this course, since this is your first course in differential equations. Some of them will be easy, some of them will be a little bit more challenging. Other piece of good news, the ones that can't be solved analytically, meaning you can't write a closed form function and say this is the answer to this differential equation. There are numerical methods to solve it, to approximate the solution, and that's often good enough in real-world applications. And third bit of good news is just as important as solving a differential equation is interpreting the meaning and modeling it in math, because that's really where differential equations come up. Differential equations are not an area of mathematics that necessarily comes up theoretically. People care about, well, what does the solution mean for the thing that I actually care about in the real world? So we'll see some of that in this lecture. We're actually, I'm going to give a differential equation that I could teach you how to solve, but I won't yet. It's not a difficult method. Separation of variables is how to solve this one. Instead, we're going to look at what it means graphically, and also some easy applications. So one thing that can be modeled by differential equations is COVID cases. I don't know if you could have imagined in March, if we're still talking about COVID cases in late September, early October. However, we still are. And let's say in Washington State, they increased by about 2% per day, which is roughly accurate, I think. So that's a rate of change, which, if you study calculus, makes you think of a derivative. So let's say the number of COVID cases is y, time, let's use t, I guess. Time is t. Great, then dy by dt is the rate of change. And it's 2% of what? 2% of the total number of COVID cases so far. So that is y. So we get 2% or 0.02 times y, or y over 50. If we can isolate the derivative like this, which is not true in every differential equation, but we often can, and write it as a function of y, and sometimes of both y and t. So another example, we could have had like 2y plus 3t. That's another example of isolating the derivative. So the derivative is some function of y and t. What does that mean graphically? Have time be positive. That means on every point y comma t on the graph, I can assign a slope. Right? Derivative is slope. Okay, so let's actually do that. And here it's only dependent on y, which actually means our function is easy. Oh, this would have been harder. But that means if I pick a value of y, let's pick y equals 100. So if y equals 100, and t is anything, t is any number, then dy by dt is going to be 100 over 50, which is 2. So I can go over here, let's say this is 50, this is 100. So I go to 100. For any value of t, I have a slope of 2. I'm just going to draw in a line with slope 2. There. I can put an arrow if I want. For everything on this horizontal line, y equals 100. Right? Because it doesn't matter what t is. That's about slope 2. And this is a sketch, so it doesn't have to be super accurate. You don't have to be plotting points or anything. Okay, that's slope 2. Now if y were 50, and t was any number. Then dy by dt is 50 over 50 is 1. Okay, so here's a slope of 1. Doesn't have to be super accurate. 1 is about 45 degrees, or for sure less than 2. Okay, and then certainly at y equals 0, we'd have slopes of 0. Okay, so I won't draw all these, but these are slopes of 0, and then we can go negative. Maybe we can't go negative for COVID cases, but there are other things, so other things that are modeled by differential equations are maybe money in a bank. We could have interest rates, which certainly depend on the current money in the bank, and then negative would be debt, money or debt. In the bank, certainly your interest rates make you go more into debt, or population growth. That I suppose you can't have negative people either. So far this is the only one that allows for negative, but let's draw this in. So y is negative 50, we'd have negative 50 over 50 as a slope of negative 1. Okay, we can draw this pretty quickly. And then let's go negative 100. We'd have a slope of negative 2. And then these aren't the only numbers we can put, right? So for any point, like let's say I went here, this is a third of the way up, so we probably have a slope of 1/3. And if I went up, you know, this would be a slope of 1/2. This would be a slope of 2/3. And so I could draw in, I could make this a lot more dense. I could draw in a lot more little lines for slope. And then what happens is, okay, now there's going to be lots of solutions. So I need an initial value. So let's say on day 1, let's say my number of COVID cases, or on day 0, at time 0, my number of COVID cases is 25. Okay, so now I have these conditions. dy by dt is y over 50, and y of 0 is 25. We call this an initial value problem. And once we have an initial value, we can get a complete solution. This is a little bit like when we integrate and there's a plus c. It's not really a definite solution unless we know what a point on the graph is. That's like this thing. We have an initial value. Okay, and then what I can do, I'm going to do this in a different color. So here's 25, y equals 25, and I'm just going to trace this slope, and at every point there's a little line, right? So I can, this is not perfect, but it has about slope 2 there, and then increases. Roughly accurate. Okay. So that is a solution curve to this differential equation, and it's the solution curve to this initial value problem. Notice I don't know what the function is yet. That's for another lecture, but here we can get a solution curve. Okay, what other solution curves can we get? Well, we can have this easy one. Let's do this, y of 0 equals 0. Okay, well if we start at 0, these are all horizontal, so we just get this horizontal line. If you don't have any COVID cases and no one with COVID cases come in, then you never have any COVID cases. That's great. That would have been nice if that were us. And then, this is not about COVID cases, but let's say we're negative, y equals, let's say, y of 0, sorry, equals, I can't see this, y of 0 equals negative 50. So I'm doing different colors. Okay, so now we start at slope 1, so this is going to increase more dramatically. So I have about slope 2 here. And then, so if we start negative, we get very negative. Hopefully, if you have a credit card debt or something, your credit card interest rates aren't this bad. This looks horrible.
Okay, so y equals 0. We call this the equilibrium solution, meaning our y value never changes. And then if we want, we can write this as a limit. So limit as t gets really big of y of t is 0. Doesn't go anywhere. Over here, so this is actually for any y of 0 greater than 0. We can look at the end behavior. Limit as t goes to infinity, y of t is going to be positive infinity. We're going to have exponential, looks like exponential. We're not sure it's exponential yet. We'll see that when we actually solve it. Growth of the COVID cases, and then limit as t goes to infinity if y of 0 is less than 0. This is for this negative case of y of t is going to be negative infinity. We don't really care where we start here. But, you know, we might start slower, here we'd start faster, but they all tend to infinity. So that's the behavior of this slope field. And so like when they talk about flattening the curve in the COVID cases, they want to change this. So like instead of actually 0.02, they talk about R0 maybe, R1. I don't remember. Okay, we'll just call it R. They'll call it 1.02 because that's what you multiply the previous day's cases by to get the new total cases. And so they're very interested in this R being less than 1. That would actually result in this number being negative. If this number is negative, then when we graph it, all the signs would point in the opposite direction, right? Instead of when we have positive values of y, we would have negative slopes, and negative values of y would have positive slopes, but we care about up here for COVID. And then if we had negative slopes, then when we started graphing our solutions, they would tend downwards. That's what we talk about with flattening the curve. Oh, okay, one more before I stop. There's a piece of terminology, so I think I said this word, but this thing is called a slope field or a direction field. Okay, so we didn't solve this differential equation, but we gave a graphical model for what it means, and we have some interpretations of how this helps in real-life scenarios.